Yes. Hello, my name is Ashley. I am a graduate student at the University of Toronto. Excited to talk to you about pulsar scintillation. So I'm first going to talk about my start in astronomy to sort of understand, I guess, my love-hate relationship with clouds. We'll be discussing in this talk. So here is a photo of me 10 years ago looking at a solar eclipse at the University of Saskatchewan. And I will have the caveat that there is a solar filter on that telescope and you should not stare at the sun without one. But I, like many people, got my interest in astronomy from stargazing. And something that someone who routinely stargazes experience is clouds. It's almost like every big astronomical event that you want to look at is thwarted by clouds covering it. So here is another photo of me, also during, let's say, the last solar eclipse, where it was quite cloudy. So I do not enjoy clouds. And so a lot of my astronomy career has been based around the idea of trying to avoid clouds as much as possible. But unfortunately, even on days when there are not clouds, we have to contend with atmospheric seeing. We have the great privilege, I suppose, to live on a planet that has air that we breathe. But when light passes through the air, it bounces off all the molecules, atoms in the air. And instead of having a nice, beautiful picture of a star, we see the light as it bounces, it makes these kind of tiny, bright images. They change in brightness, they might change in shape. It makes the image look really weird. And this phenomena is called atmospheric seeing. With our naked eye, you can't usually see these individual images. And so what it actually looks like with our naked eye, just looking into the sky, is that you see twinkling. So here's, a really dramatic version of it, but the night sky, you can see the constellation Orion. There's lots of stars. The ones that are closer to the ground twinkle a lot more because they travel through a lot more air, and the ones higher up, not so much. But there are two notable exceptions to this rule of stars twinkling or things in the night sky twinkling, and that is in this image, you see the moon and Jupiter. And the moon and Jupiter are different from the background stars in many ways, but for specifically this point of twinkling, the reason they are different is that they are much, much closer. Okay, so it's sort of a generally known rule that planets don't twinkle while stars do. And that's kind of a quick way you can tell if you're looking into the night sky and you see something twinkling, it's probably a star. And as far as the atmosphere cares, it doesn't know what sort of object is in the sky. It only knows that if something is very small, it appears like a point, then it's able to do these optical effects, this seeing that makes the light interfere and causes it to twinkle. If you've done any sort of optics things in I don't know if you've taken high school classes with optics, then you'll know that sometimes things work with lasers that don't work with flashlights. And that's because lasers are small, flashlights are big. Similarly, stars are, well, physically quite large, but far away, so they appear small and planets appear much bigger. There's several things we can do to avoid the atmosphere. One is, of course, to send a telescope to space. So here's an example of some galaxies taken with a telescope both on the ground on the left and then with a telescope in space on the right. And you can see that the image appears much clearer. You see a lot more detail in the space image, and that's because there's no atmosphere. You don't have that atmospheric seeing. Beyond that, the amount of seeing or how light interacts with gases, it depends on the color of the light. And that's because different light of different colors has a different wavelength. So here's an image showing the different sort of categories we have for light. And if you think of light as traveling as a wave, then at the very far end, we have long wavelength where the distance between these peaks is much different, or much larger. And then on the far left, they're much closer packed. And so this is essentially saying how big is the light for how the atmosphere sees it. And different colors react with the atmosphere very differently. Here's an image showing how much light is going to be absorbed by the atmosphere based on different wavelengths. So on the far left, we have the very short wavelength, the gamma rays, X-rays, UV, basically completely blocked, which is great for us with DNA because that's can cause cancer, and that's why we wear sunscreen. And then we can see some, but not all visible light. It gets a little distorted, hence we see the seeing. And then there's longer wavelengths, and you see this nice, beautiful gap of a few centimeters to a few meters, and that's the radio spectrum. And that's what kind of astronomy I look at. And so instead of sending telescopes to space, we have them on the ground, but we look at particularly wavelengths where the atmosphere doesn't matter. So I did it. I solved the clouds problem. I never have to deal with it again. Incredible. So here's more pictures of me at various radio telescopes that I've visited throughout my career. And I mostly want to illustrate that radio telescopes come in a bunch of different shapes and sizes. Most of them sort of look like antenna that you might have for a TV or something, because, I mean, television is radio waves. But I also want to point out a couple pretty weird ones, which are like in this field, you see a bunch of sticks. And in this picture, you also see a bunch of sticks. And the cool thing about radio astronomy is that all you really need is a big stick of metal, and it will interact with the radio waves to get a signal, which is cool. There's also several of these telescopes are in Canada, particularly the one in University of Saskatchewan, the Algonquin telescope, and CHIME, which is in British Columbia. Okay, so all these things are cool, but what does it actually mean for what things you look at in radio astronomy compared to the different wavelengths of light? So here are two images of the sky. This is showing everything that we can see in the galaxy. The galactic center, so in our Milky Way, is sort of in the middle here. If you've been outside on an incredibly clear day, far from light pollution, you might recognize that this sort of strip in the middle looks like the arm of the Milky Way. That's because it is. And so on the left, we're seeing the visible sky. You see lots of stars. And that's basically the majority of what you see in that image. But in the radio sky, you don't see stars. You see these very large extended features. It's quite bright around this galactic plane in the middle, and then not so much out to the edges. And so you're looking at just very different things. Now, there are some things that exist in the radio that are point-like. They look like stars. And one of these is the quasi-stellar object, which is named specifically because it looks like a star. It is star-like. These are actually very distant galaxies, but they do behave very similar. If you were to see like a map of the sky in quasars, it would kind of look like seeing a bunch of stars. There are pulsating stars, pulsars, which I will talk about more in detail, and fast radio bursts. These are very far away from different galaxies. We don't actually know what causes them, but for my purposes, the only detail we need to know is that they are point-like. Okay. So if one were to look at the sky, instead of seeing the stars as all your little points, what if you looked at the pulsars instead? And this is what it looks like. This is kind of the position of all the known pulsars in our galaxies. They are very much in the same sort of regions of the sky as the stars are. So where the image on the left is bright, it's also bright on the right image. And so if you were wanting to do something like stellar astrophysics within the radio, this is what you would look like. Okay, so what actually is a pulsar though? So unlike the quasi-stellar objects, a pulsar actually is a star. But it's a little bit more detailed than that. It's specifically a neutron star, which is of a category of dead stars. So to get a dead star, one first must have a living star. And so in a living star, at least a very baby star, it's made mostly of hydrogen, and in the center of it, it's going to be taking hydrogen, like one hydrogen atom and another hydrogen atom, and smashing them together to get a heavier helium atom. And as the star lives its life, it's going to smash heavier and heavier elements together until you eventually end up with iron at the core. And iron is special because smashing it together doesn't create any energy, and so it basically means that the star can no longer create light, create energy, and will begin to collapse. And so shortly after a star has an iron core, it is going to explode in something that is called a supernova. And in that supernova, all the outer layers of the star are thrown off, and you're left with just the core. And that core will still collapse, and it'll collapse quite strongly. The pressure of that is enough to cause a process called neutronization, which is when the protons and the electrons within the core squish together and they make neutrons. And this is sort of leading into where the neutron in neutron star comes from. So when this core collapses, there are three possible options for what happens. One is it forms a black hole, which is it like collapse until it cannot collapse physically anymore. It's the densest thing possible in the universe. Or it might not collapse quite as much. Let's say the star that began this was not quite as heavy. In this case, it's left with a core, but it's entirely made of neutrons. And that is then a neutron star. There's also a third option where instead of collapsing, it just sort of explodes and nothing is left at all. So here are two examples of what is left over from a supernova. This is the outer shell of that star thrown off. You get all these really cool gas, like the bright splotches in these images are the gas that's been thrown off from the outer edges of the stars. And in both of these cases, there is a neutron star in the center. The images I'm showing are mostly in optical and X-ray light, so you don't see the pulsar because it's in radio light. But I promise you there are neutron stars or pulsars in these images. Okay. So there's a lot of cool things about neutron stars because they've taken this star and collapsed. You've taken what was like the core of the star was something like 1 to 2 times the mass of the sun, and then it collapsed it to be a sphere with a diameter of about 26 kilometers. So that's, I mean, very, very small. And that means it has densities that are huge, 10 to the 18 kilograms per meter cubed. There's a number of analogies people make. They're all going to be kind of impossible to wrap your head around. People will say it's like having an elephant held in a teaspoon. It's like that much weight in that small of a space. They're also very hot because of all the smashing of atoms together. You get a lot of heat. So they start off being several million degrees, and then they cool down over time to be only a few 100,000 degrees. They also have a huge magnetic field, which is something like 10 billion to 10 to the 17 times larger than the Earth's magnetic field. So the consequence of having a magnetic field that large, and I guess if people were at last month's AstroTours, this is a little bit less than the magnetars, but what happens is that you have this magnetic field around your stars, and these sort of black lines are showing what the magnetic field looks like. And And at the north and south poles, all the gas and stuff that's around this neutron star gets accelerated out by the magnetic field. And what happens if you have accelerated charged particles? They create light. And so you have these bright beams of light that are only coming from the poles of the neutron star that allow us to see it. So why we call them pulsars, or what makes pulsars different than like any specific neutron star, is that they appear to pulse. And so they have these bright jets that are coming from the poles, and as the star rotates, the jet can point towards us or away from us, and we only see it when it's pointing towards us. They also spin really fast, a few seconds to a few milliseconds. And so once every second or millisecond, you're going to see this little bump in the brightness of, what you were looking at, the pulsar. And what's really cool about having something so dense that's spinning so fast is that it's pretty hard to slow down. And so the rotation period is going to be the same within a nanosecond for every rotation of this pulsar for several hundred years. Like it slows down over time, but incredibly slowly. And what we can do with that is measure the distance to this pulsar very, very precisely, or like changes in distance, because light travels something like 30 centimeters in a nanosecond. So if you measure something within a nanosecond, you can tell if its distance has changed by 30 centimeters, if the time between the pulses changes by 1 nanosecond. So a common instance where this would be applicable is if your pulsar is in a orbit around another star. And so you will see that as the pulsar moves around its orbit, if it's moving towards you, the pulses are going to start arriving closer together. So that's, I guess, this instance at the bottom. If it's traveling away from you, they're going to start being farther apart. So here's like this big gap. And then they start clustering together again and farther apart, kind of like a slinky. And so you can measure the rate at which this comes, you can model it, and so you can figure out to great detail the orbital parameters of this pulsar, like how it orbits around some other star, which allows you to tell a lot of things about the system. Another example of something where a pulsar might be moving in space is a response to gravitational waves. So in a similar way to how these charged particles are going to create light when they are accelerated, so they're creating, in this case, electromagnetic waves. You can also have, if something is massive, it has mass, it's moving around, accelerating, it'll create something called a gravitational wave, which is going to stretch space in different directions. And so on the right, that's showing a bunch of little points. If you had sitting in a gravitational wave, they're going to squish together in one direction and then pull apart in the other direction. And then as it moves through, they'll switch direction is the one that gets squished. Okay, so if we imagine that all these little points are pulsars, then we could create something that's called a pulsar timing array, where we measure the times for the pulses of many different pulsars, and we see, are they squishing towards us in a way that it's like multiple pulsars in similar directions are squishing towards us at the same time, while others are pulling away. And then you'd expect it to change later, that the ones that were pulling away are now squishing towards you. And this has taken several decades, but as of last year, it became possible with pulsar timing arrays to measure gravitational waves. And this is something, people are still working on and trying to improve, but it's a very interesting application. Now, all of the little pulses I've shown so far have been very pretty. One point, it goes up, it goes down. But that's not really true of what pulses look like in reality. So I have on the left here, these are pulses from several different pulsars, and each pulsar has its own unique shape. Some of them do have just one up, one down. Some of them will have one and then like a big break and then another one. Some of them will have several little pulses kind of all clustered together. And so it's harder to define in these cases. When does this pulse arrive? When it's all weird shaped. And another problem is that it depends on what wavelength or color you're looking at the object. The pulsars will have different shapes to their pulses depending on what you're observing. So that's the picture on the right is showing how they look different at different wavelengths. Okay, now we have returned to my enemy, the interstellar clouds, because unfortunately, part of the reason that these pulses look so different is because of how they interact with clouds in space. So they're interstellar because there's stuff that exists between the stars that is not stars. And so we've actually seen some of this previously in this talk. Here are examples of interstellar clouds. We have big clumps of gas caused in this case by supernovae that exists between stars and is not a star. There's been other examples I've shown. I showed the whole what the sky looks like in visible light. And some of you may have noticed is that there are patches where it's a lot darker where you don't see the stars like here. And that is because there is some big cloud of gas that is blocking all of the light from us. If instead of looking by how much light is blocked, we look at how much light the clouds themselves are giving off. There's an example on the right. You can see basically any bright thing on that right object is some form of interstellar cloud. So there are a lot of them. They're kind of everywhere. And they're also roughly in the same like region of sky where stars and pulsars are. And so it means that it interacts with the light that we're trying to observe from the pulsar. There's a few ways it does this. One is through a time delay. So this is something called refraction, which is that when light goes through some sort of object, other than the complete vacuum of space, it's going to be slowed down. And so the light arrives later than you would expect. And that refraction depends on wavelength. And so depending on what color you're trying to observe, it'll arrive at a different time. So some colors are going to arrive sooner and some will arrive later. This is the same physical process that causes light to split in prisms. So I guess if you've seen like the Pink Floyd cover or actually just, observed light going through any sort of glass, it'll split into rainbows as the light gets differently refracted. In pulsar astronomy, we refer to this effect as dispersion measure. It's just like the number that tells you how different the colors are going to arrive compared to each other. If we look at this instead with when the little pulses arrive, you're going to see like some pulses arrive sooner, and then you'll see another pulse later if you're looking at a different color, and later. Now, typically when we're looking at this, instead of looking at discrete pulses, we'll sort of try to look at all of the colors at the same time. And so that plot looks more like this. So this is sort of still showing it's going to be a short wavelength at the top and long wavelength at the bottom. And you see now the brightness of this image is where the pulse arrives, or like how bright the pulse is. And you can see this very distinct sweep, like line as the pulses arrive later and later with different wavelengths. Okay, so that's something we can measure that tells us a bit about the cloud. But all of this light is going straight through the cloud and arriving at us. But it also, similarly to atmospheric seeing, has the option of bouncing around on the different atoms in the cloud. And so the consequence of that being it makes multiple little images of your thing. They have different brightnesses. and it appears to be a different size depending on what color you're looking at. So if you had an original image that it's like all the colors are all the same shape, it's point-like, then when you observe it at the end, the longer wavelength, like red light, is going to appear larger. And then in the shorter wavelength, it's going to appear smaller. This also has a consequence for when the light arrives to us, because the more it's scattered, the farther the light had to travel and the longer it takes to arrive. And so again, instead of having a nice peak that goes straight up and down, it has this very long tail, so that sometimes it arrives quite a bit later, the final light from that pulse. And that depends on the wavelength. So all these images on the right are for the same pulsar, I think. And they are arriving, it's like much wider at longer wavelengths than it is at shorter wavelengths. Okay, now this also means that we see twinkling in the pulsars. And when we see it in radio astronomy, we call it scintillation. So this image is showing, instead of individual pulses, you're saying how bright on average is a pulse. And maybe this is a little harder to interpret, but if you were to say something is twinkling, that means it gets bright and then dim and bright and dim over like some sort of time period. And so we see this, in this case, the dark spots are where the pulsar is bright, and then the like lighter gray are where it's not. And this also depends on the frequency or the wavelength that you're observing the light at. And so this sort of, if you observe this, is very characteristic of scintillation. And another way that we sometimes describe scintillation is with this analogy of light bouncing off of a lake. In this case, I hope you're familiar, this is the Toronto city skyline as observed from the Toronto Islands. And you can kind of see the light from all the buildings as it bounces off the lake. You see multiple images, they're sort of spread out in way, like along a line, and they have different brightnesses at different points along this line. And so if you were to observe your pulsar and you could see all the individual images that are formed, it would look something like this sort of line with all these little speckly bright spots. Yeah. Now there's a number of things we can measure from observing the scintillation that tell us about the stuff that's causing the scintillation, like what are the clouds doing? So one is saying, based on how much the delay is between the pulses or the light that first arrives versus the light that arrives last, how long that time takes, tells you about the distance to the clouds, because it tells you how much farther the light had to travel if it went along this like longer path than the one that comes straight to us. We could also tell from the twinkling, like how long a period of brightness is. We can tell you how quickly everything is moving relative to each other. If the cloud and the pulsar and the Earth were all traveling together, then we would still, see bright spots, but they wouldn't change with time. They would only depend on wavelength. And so typical speeds of these things, the Earth, as it rotates or orbits around our sun, it's going at 30 kilometers per second. The clouds are only going something like 20 kilometers per second, but the pulsar may be going very fast because it is born in an explosion. And so it happens to just like fly off in this explosion, something like 1,000 kilometers per second typically. But we can measure the exact quantities if we know like a specific pulsar and its position and stuff. We can measure then the velocity of the cloud, which there's no other way to measure the velocity of the cloud without the scintillation. Okay, the last thing you can measure, or last two things, I guess, you can measure about the clouds is the angle that it makes between the light that is scattered in the cloud versus the light that is not scattered. And that tells you how big the cloud is, like how how far a light can travel along the cloud where it still gets scattered before there is no more cloud. And we know from this that typically the clouds are something like a few AU, where AU is an astronomical unit. That's the average distance between the Earth and the sun. It's hard to to say, like, distances in astronomy are crazy, but as far as clouds or structures we see in gas goes, this is very, very small. It's large compared to us humans, but it is small for gas. And to put that into perspective, we see all sorts of stuff in gas, going on different orders. On the very left is sort of the largest scale. That's our whole galaxy is something like 8 billion AU across. And we see large structures. There are spiral arms to our galaxy. And so you could call, I guess, that all a gas structure. The longest sort of filament structure that we see, or I don't know, thread that we see in the gas is something like 250 million AU. There are sort of molecular clouds, the regions where stars are formed. Those are something like 250,000 AU. We have the very well-known pillars of creation. And the smallest scales that we measure with telescopes are something like 100 AU. And these are showing different disks around stars that are forming, and they're forming planets within those disks. But we actually have no idea what is happening at scales of 10 AU. And that's because that scale is far too small for us typically to measure with a telescope. And the only way really that we can do that is with scintillating, with measuring how distant point-like objects are affected by the light. So that brings me finally to what I do for research. And so to put this, I guess, succinctly, what I do is I yell at clouds. And particularly trying to figure out what are the clouds that are doing this scintillation like, and why. So I return to both hating and loving clouds. And we actually don't know for the most pulsars what sort of clouds are causing their scintillation, but there are a handful of cases where we do know. And most of those are very close to the pulsar. And so the ones on the left, I guess, the top, the supernova remnants, that's because the pulsars are formed in supernova remnants. They're surrounded by gas, and that gas has the ability to alter the light that we see from it. There's also something that pulsars can do as they move incredibly quickly through the gas is you get something like a sonic boom that'll form around them. So you get these shock waves, which are called bow shocks, in front of the pulsar as it moves. That is just like mashing gas together. And so it's able to also cause the light to be affected. Another thing that we know is that when pulsars are sort of behind the sun, we see scintillation more. And so we know that this is a result of solar winds. So when the sun is like throwing off gas, we see more scintillation. And then there's only one really confirmed case that we know of something that is causing scintillation that's not directly at the pulsar or sort of directly near us, like the sun. And that's in something called an H2 region, which is hot gas that surrounds a star, any sort of hot star. But yeah, this ultimately ends up being like 5 pulsars that we know what is happening. And so what I specifically do, I mean, I say there's only 5 that we know what's happening, but it's also true that there aren't very many pulsars where we've really measured the effect to know what the clouds, like the properties of the clouds. And so I do all this taking these images where we see how the brightness changes with time, and I figure out the distance and the velocity of the clouds. You can also tell something about the shape of the clouds by which direction it tends to scatter. And so on the right, I have a plot that shows all of the screens that we know. Each of the colored lines are the directions toward pulsars, and the little dots are where the screens are, and the arrows are which direction the velocity of the screen or the cloud is. This is all limited to within, I think, 10 million AU. So it's actually relatively close things. And yeah, you can tell just from looking at this, there's only something like 20 where we know these measurements really well. Okay, but even though we only know 20, something I've tried to look at is comparing with gas that we see. So on the background, the colors are showing like how bright gas is. This little circle is where a pulsar is, and this line is the direction that we see scattering. And right about now, you can see that there is gas that's very well aligned in this direction for this particular pulsar. And that's been something I've spent the last couple of years at, is looking at different emission or like what is happening from the gas to see, does it actually have the same shape as we would expect from the scintillation that we see? And the answer seems to often be yes. I'll just switch to like a still from that thing. Now in a different color scheme, but you see, right? Like this is the line and there is brightness in that line behind it. But something to keep in mind with this is that this scale is much, much larger. This is something like 100,000, no, well, somewhere between 100,000 and a million AU, this structure that you're seeing in the gas, compared to the 10 AU that we're actually seeing that is causing the scintillation. So it's quite interesting that you still see gas that's sort of in the same direction, even though it's far, far larger. And that's something I'm trying to figure out. So the last thing I want to show everyone is this plot that I made that I think is cool. This is another way of showing all of these. Oh, has it slowed down? There we go. All of the pulsars. Okay. Still, sorry. Okay, it's taking a while to load. It's showing all of the pulsars as before, the lines being the direction of the pulsars and the dots being the screens. And this weird pink blob being a supernova remnant that we live inside of. So the Earth is at the center there. And I believe 100 million years ago, there were several supernovas that happened all in the same area, and they made this really funky shaped blob of gas. And it's hard to sort of say what that specifically means for scintillation. This is definitely the largest cloud within our vicinity. And a lot of the screens, if I zoom in, or the clouds are inside of this purple or the pink blob, which is a little strange because a lot of the gas has actually been thrown out from the supernova remnants. But I think it's interesting to put these clouds in context. They're actually much smaller and much closer than the closest, largest cloud that we can see. And that's all I have for my talk if we want to move to questions.
Okay, I'm going to field questions up here, and then I'll pass them along.
Sounds good.
Hey, that's very sun, very bright. Yeah. So, does anyone have any questions? And then I will repeat them to Ashley to try to get this audio across. Yeah. So, theoretical spatial resolution with all those other spatial resolution. Yeah. Ashley, were you able to hear that? Or
Well,
okay,
half
so
of it.
To paraphrase a little bit, the theoretical threshold for what we could really see in terms of motion is, I believe you said 30 centimeters. So considering all the other effects at play, what's sort of the practical threshold for what sort of motion we could detect?
Yeah, that's a good point. So I said,
One sec. Sorry, you're muted. There you go.
okay. Yeah, so yeah, from the pulsar end, it should be within a nanosecond, but given all the other effects, we can only measure something like microseconds, so it would be 1,000 times larger. But you're still like, that's kilometer that you could measure.
Pretty precise, astronomy.
Yeah, the size of the thing is 26 kilometers, so it's like still within, it hasn't moved outside of its shape.
Any other questions? Yeah. Another big question. So how much variation is there in the composition of the gas? And is that something that we can measure? And how does that affect the dispersion that we see?
Ooh. Yeah, okay. I'll maybe, yeah, split that into two questions. So what's difficult about the scintillation is it actually only cares how many electrons are in the cloud. So we don't know anything about like element wise what it is. The images I was showing with the lines, this is hydrogen gas, which is, I guess, a good guess because almost everything in our galaxy is hydrogen. But yeah, we can't tell elementally what it is. But in terms of dispersion measure and stuff changing, like we can tell how the cloud changes on scales of a few minutes. That's like this, how it changes as we move across it. So there's clearly something happening in terms of how many electrons are happening on even smaller than AU scales. And the dispersion measure, oh, I don't know if I can put that into like human units. It changes by something like 1 in 1,000 over a few weeks, typically.
Any other questions? Yeah. Sure. Sure. So the question was basically, where are the jets in a pulsar originating from? If most of the material within the neutron star is neutrons, how do we get these charged jets?
Yeah, okay, yeah, very good point. Neutrons are not charged. So that's also something that isn't known totally. Somewhere in this sort of region where the magnets are, a neutron star actually has its own atmosphere. It's not a very big atmosphere. It's mostly, well, I'm not sure even if we totally know the composition. It's often like hydrogen and helium, and sometimes carbon. And so some of that gas can then get accelerated by the magnetic field. It's not coming from like the compact neutron core.
Any other questions? Probably have time for one or two. Okay, if not, help me thank Ashley again